So this is the model that we'll typically use, which is we're just going to think about bonds as being an overlap or a sharing of electrons from atomic orbitals. In the localized electron model, we have lone pairs, so these are pairs of electrons that are localized around a particular atom, and then we have bonding pairs, which are the ones that are shared between different atoms and are assumed to be located in the space between the atoms, at least in terms of one type of bond, which we'll find out later is a sigma bond, but we'll get to that in a little bit. The model that we're going to use to predict the geometry of molecules is abbreviated as VSEPR, the valence shell electron pair repulsion model, which simply says or means that pairs of electrons will maximize the angle from other pairs of electrons to assume the most stable shape. And in order to come up with the information about a particular covalent molecule, then we will write out the Lewis structures, which shows the bonding and the non-bonding electrons that are involved. Most of the Lewis structures that we're going to draw will actually follow the octet rule, but there are a few cases where there is a different sort of rule that's followed, or a different type of bonding arrangement. So one of these is with hydrogen, which becomes stable when there is just a shared pair of electrons. And again, most typically we're going to be looking at molecules that follow the octet rule, and that is that each atom is going to bond and achieve the octet. In other words, to have 8 electrons, either through sharing or through its lone pairs of electrons, and that's going to be the most stable structure. You may recall that the line represents a pair of electrons, so that's considered a bond, and a bond is a pair. We can also have double bonds, so this would be 4 electrons, or the way we usually describe it is 2 pairs of electrons. Okay, so 2 pairs of electrons, so that's a double bond. And we can also have a triple bond, which is 3 pairs of electrons. So these are the steps that we're going to use to write Lewis structures. We're going to, first of all, add up all the valence electrons from all the atoms that are involved. We're going to use a line to represent pairs of electrons between atoms, and we're going to assume that other than hydrogen, that the atoms are going to achieve noble gas configurations. So to pick a simple case, if we are looking at the Lewis structure for H2O, we have 2 electrons, 2 valence electrons, 1 for each hydrogen, and then we have 6 for oxygen. And if you look, you can see that you can get that quickly from the periodic table, that hydrogen is in the first column and oxygen is in column 16. So if you take that second number, the 6, then that gives you the valence electrons. So that means that we have 8 total valence electrons. So we have the situation where we put oxygen connected to a hydrogen, and that's a pair of electrons, so we've used 2, and then we have another pair of electrons there, so we've used 4 of our 8 electrons. Then we have 4 more electrons, so we put a pair of electrons around the oxygen here and another pair of electrons there, and now we have hydrogen is stable because it has 2 electrons, so each of those has 2, and then we have the oxygen, which has 8, so it's 2, 4, 6, 8 electrons. And we can also draw similar examples for PBr3 and HCN, and we'll do much more practicing of this as we move along. So in this case, we already did hydrogen, so the Lewis structure for hydrogen is just going to be H. For fluorine, we're going to have a total, so each fluorine is 7 electrons, so we're going to have a total of 14 electrons. And if we have a bond like that, and then we add in the remaining electrons, so each fluorine atom gets 8, and we have used the total number of electrons, so 2, 4, 6, 8, 10, 12, 14 electrons. HF, we're going to have 8 electrons, so HF is just going to look like this. So we've used 2, and then we put the additional electrons around like so. So some of these I think it would probably be useful for us to work through in class. So we'll work on these in class. You should go ahead and do them yourself first, and then we'll take a look together and see how to work these out.